Alright, you sexy beasts. It is Brandon here. Alright, so this question is from the Specialist Mathematics IA2 paper, question 1. Now, here we are given a position vector function for the particle given by r equals 3 sine ti plus 4 cos t of j. Now, part A says use an algebraic method to show that the corresponding Cartesian equation of the path of the particle is given by 16x squared plus 9y squared equals 144. Now, so I'm going to write down this little equation, 3 sine ti plus 4 cos t j. Now, we've got to turn the i's in the j, so the imaginary plane, into the real plane, the Cartesian plane, x's and y's. Now, we should all know that we call it component form, so turning i's into x's and then j's into y's. Now, to do this, we let x equal 3 sine t, and we've let y equal 4 cos t. So obviously y will correspond with j, x will correspond with I. Now we can rearrange this to get them in both terms of t, because as we can see, both these functions have either a sine or a cos of t. So if we rearrange it, we can have sine of t, and we can have y over 4 equals cos of t. Now, this question is very difficult purely because you need to know a lot of little mathematical details, a lot of formulas, but most of them are on the formula sheet. So, with this, you have to recognize a Pythagorean identity that sine squared t plus cos squared t is actually equal to 1. This is a very important formula that you'll need to know to do this question. Now, here we have a sine t and we have a cos t, all right? So we can apply these two, I would say models, to this larger model. So, if we go x over 3, that'll be sine t, but it's squared, so we can square it, plus cos of t is equal to 1. All right, perfect. So now we've got the x's, we've got the y's, we've got a left-hand side, we've got a right-hand side. So this is looking much, much better. So if we open this up, we've got x squared over 9 plus y squared over 16. Remember to square both the top and bottom, and that will equal to 1. Perfect. So, next page. All right. Now, we're very close. We've got an x squared, we've got a y squared, we've got a 9, we have a 16, but we do not have the 144. Now, to get the right-hand side of this equation and this equation to equal 144, we obviously would times this side by 144. But we cannot only do that to one side. So, if we times this by 144, we would have to times the other side by 144. So, if we write this, this will equate the terms. Now, if we open up the brackets, we'll have 144 x squared over 9, so that's a plus, so that's a y. Jeez, my writing is terrible, sorry. 144y squared over 16. Now, we simplify these fractions. We'll go up here to do it. 144 equals 16x squared plus 9y squared. Now, this equation looks identical to this equation. So we have proved that this model, by using Pythagorean identities, can form a Cartesian equation of a certain particle. All right, so that question's done. We'll go on to question B. Now, question B says, use the Cartesian plane below to sketch the graph of the particle, including its direction and motion, and communicate the development of your sketch. So let's have a look at this. All right, now this one is a tricky one, so we'll work through it a bit slowly. All right, so we're using a Cartesian plane, which means we're not using this specific model as such, because this uses i's and j's. We need x's and y's. So from the question before, we'll use the same x and over 9 plus y squared over 16 equals 1 equation. So then we can use it in a Cartesian form. Now, this is again one of those little mathematical facts that you need to know. But this is actually got something which I'll show you. A squared equals y squared over b squared equals to 1. Now, this and this are the exact same. So this is a squared, which would be 9. So obviously that would be 3. A would equal 3, and then 16. B would equal 4. Because it's 4 squared 16, 3 squared is 9. Now, this equation here is actually an ellipse. So an ellipse, obviously being like that kind of shape. It's like a flat circle. So if we actually have a look down, if we have a look at the graph, I'll draw it. Now, there is a few little facts you will need to know about an ellipse. Okay, so whenever you have either this could be on x-axis or the y-axis, your furthest distance between the 2 points on one axis is called your major axis, because it is obviously major, it's bigger. Something like this, the small one, we would call your minor axis. So just some fun facts there. So this here would be negative a0, this being a0. This would be 0, negative b, and this would be 0, positive b. So if we have a look back up here, have a look with our the equation that we had before and the ellipse equation, we can see that a squared equals to 9 and b squared equals to 16, which therefore means b, oh no, oh god, sorry, jeez. You can see that b is equal to the square root of 16, which equals 4, and then the square root of 9 equals to 3. So we know our x, so obviously negative a and positive a, so we've got negative 3 and positive 3, and then with b we've obviously got your negative 4 down here and your positive 4 up down there. So if we rub all this out, oh god. Alright, let's have a look. So we've got that. So this should be pretty easy to graph. So if we scroll down here, so if we go, obviously A is related, or rather A is related to our x-axis, B is related to our y-axis, purely just from the Cartesian equation. Now, have a look. So we've got positive 4, so we've got 1, 2, 3, 4. So we have a point up here. We have a negative 4, so 1, 2, 3, 4. All right, B is plus minus, and that's plus minus. And then we have plus minus 3 on the x-axis. 1, 2, 3, 1, 2, 3. All right, now I'll attempt to draw this. Oh, God, this is shocking, but I think you understand the gist. Imagine that as a flat circle. So we've got those. Now, we have graphed it. You can draw the points on there if you want to. Obviously, this would be what? So that would be 0, 0, 4. We've got a point at 3, 0, negative 3, 0. And down here we have 0, negative 4. Perfect. So we've drawn it. Now, here is the another thing, obviously another mathematical reasoning. So we have sketched the graph, but we need its direction and motion. Now, to do that, if I can draw, to do this, we'll sketch this out, sorry. To do this, we need to get the original equation back. So obviously, we'll reduce this to cast. Now the truth. No, that's not right. Hold on. Oh. So, if we have a look at the original equation, we've got r equals 3 sine ti. So, r equals 3 sine ti plus 4 cos tj. Now, to find its motion, its motion and direction, we can sub in values of t to find y, and that would give us our motion, because this is obviously this is a position equation. So let's say, for example, we sub in t as 0 to find its r value. So we have r0 equals to 3 sine 0. We'll just disregard the i's and j's for now. Plus 4 cos 0. So this is when, obviously, t equals 0. So we're looking up here right now. Sine of 0 is obviously 0. And 3 times 0 is 0, so it'll be 0. Plus 4, so cos 0 is 1. Plus times 4, that'll be 4. 4. So we already know this point of 0, 4. So this confirms that what we're doing here is right. You don't need this step, but it confirms it. So let's do something else, but let t equal a different value. Let's sub in t as let's sub in t as 1. Okay, so then we got 3 sine 1 plus 4 cos 1. Sine of 1. Pretty much you'd need a calculator to find sine of 1, but this ends up equaling 3. So at 1, we've got a point at 3. Now, if we sub t then as 2, we'd get a answer of x about of r about down here, which means every time that you move right, you will have every time that your t is increased, your r will increase as well, which means we're going this way. Obviously, you'll hit a certain point. If you let t equal, let's say, 4, you won't get an answer. It just won't happen because it's not in your domain. Obviously, if you let it, let's say, equal t equals -1, then we've got a direction and motion this way. But so far, this is our direction and this is our motion. So this would be your graph, obviously labeled, and then the direction / motion would go from top clockwise. That's about it. So yeah.